Good morning, friends. In this video, we are going to discuss about the voltage divider bias circuit. So, in last video, we discussed about fixed base bias circuit. There is only one resistor RB. Here, there are you can see there are two resistors R1 and R2, and there is one additional emitter resistor also there. We will see what is the significance of these resistors. First is we have to find the operating point, DC load line, and the Q point. For this, we have to draw the DC equivalent circuit. To draw the DC equivalent circuit, we have this capacitor, coupling capacitor is act as a open circuit. So this is open. This input signal is decoupled from the remaining circuit. So we will get only R1 and R2 on the remaining part. Now this we are going to draw the Thevenin's equivalent to this base. So this is plus from here to here. That is, we are going to draw the Thevenin's model to the Thevenin's equivalent to the base circuit. That is shown here. BTH and RTH. So how to get this? This is VCC. This is R1 and this is R2. So what is VTH is? This is VTH. The voltage across this R2 is Thevenin's voltage, which is given here. So what is VTH is? Total voltage R2 divided by R1 plus R2. So this is Thevenin's voltage. How to get the Thevenin's equivalent resistances? To get RTH, you have to make VCC to be 0. So if you make this VCC to be 0, that is if it is grounded, then this R1 and R2 becomes parallel. So RTH equal to R1 parallel R2. So we got VTH and RTH. Now the first thing is, this is the load line and this is VCE and this is IC in milliamps and this is the load line. So now we have to find the endpoints of this load line. For that, I am write KVL at the output loop. So here, so that is minus VCC plus ICRC plus VCE plus IERE, that is equal to 0. So here we know that IE equal to IB plus IC. I want to write everything in terms of IC. So I can write IB as IC by beta plus IC. So IE equal to IC multiplied by 1 plus beta divided by beta. Coming here, minus VCC plus IC, which is IC multiplied by RC, plus instead of IE, I am writing this, which is 1 plus beta divided by beta RE plus VCE equal to 0. Now we know that how to find the endpoints. First one is set IC equal to 0. If you set IC equal to 0, VCE equal to VCC. So this point is VCC. What's the second one? Set VCE equal to 0 volt. If VCE equal to 0, what is IC? VCC divided by RC plus 1 plus beta divided by beta RE. So I can write what is this point is VC divided by RC plus 1 plus beta divided by beta RE. Now we have to find the Q point on this. For this, I am going to use this circuit. I will copy that. Now write KVL at the input loop. That is the base emitter. This point minus BTH plus IB RTH plus VBE. VBE is here plus minus this point is VBE plus IE RE equal to 0. So we can write IE in terms of IB. IE equal to IB plus IC, IB plus beta IB, that is equal to 1 plus beta IB. So now it is minus VTH plus IB RTH. Instead of this IE I can write plus 1 plus beta RE plus BBE equal to 0. So I want to find at quiescent point, I can write operating point IBQ equal to VTH minus VBE divided by RTH plus 1 plus beta RE. So once IBQ is calculated, I can get what is ICQ, that is beta IBQ, that is equal to beta multiplied by VTH minus VBE divided by RTH plus 1 plus beta RE. Now we got ICQ. Now I want VCQ. For that VCQ, I have to write the KVL at the outer loop. So already we have the KVL at the outer loop. We can take the same thing. Now we can see the KVL at the outer loop. So this is the loop minus VCC plus ICRC plus VCE plus IERE equal to 0. So from this we can, instead of IC I can write ICEQ. Here I can write VCEQ at Q point. So VCEQ equal to, which is VCC minus ICEQ RC plus 1 plus beta divided by beta RE. Now we got the Q point, VCEQ and ICEQ. We can plot these points here. So it can be anywhere on the load line. So this is VCEQ and this point is ICQ. So now we have derived the steps for getting the Q point. Now we will discuss what is this advantage of having the voltage divider bias. If you see here, I have written what is IBEQ and ICUQ here, whatever we have derived it now. What do I expect from a biasing circuit is, even though there is a variation in beta, it should not affect the value of IC much. That's what we expect. So what happens is, whenever there is some due to some temperature, increase in temperature or some slight variations, increase in VCC, it may tend to increase in the collector current. So increase in collector current leads to increase in the emitter current. This emitter current flows through this resistor RE. So what happens when IE increases? The voltage across this resistor, which we can call it as VE, which is voltage across this emitter got increased. So VE is increased. Now this is R2. The voltage across this resistor, you will call it as, this is the base voltage. The voltage across this resistor R2 is the base voltage. We know that what is VBE? VB minus VE. So VB equal to VBE plus VE. So now I1 is the current flowing through R1 and I2 is the current flowing to R2. And IB is the current into the base. We have to assume that, we have to take that this IB is very much small when compared to I1 and I2. So in such case, BB is the voltage across the base, that is from here to here. This is the voltage across the base. Voltage across the base can be approximated as voltage drop across this resistor R2. So it is approximately IB I2 R2. Now we know that what is VBE? This is the base voltage across the base. VB is BB minus BE. So VBE can written as BBE plus BE. Now what happens if V increases? If V increases, this VBE drops down. This VBE drops down, bring VB also down and IB also down. So the increase in IC is now compensated by this decrease in IB. So IC equal to beta IB. If IB increases, IC will also increase. That is the initial problem. Now, because of this emitter resistor, which creates this potential drop VE, this increase in this VE, because of this increase in this potential drop VE, there is a decrease in VBE. So the base voltage comes down, which brings the base current also to comes down, and then collector current also is reduced. Now this is how the emitter resistor helps to. This is how the emitter resistor helps to provide a negative feedback. Now, if you, from this equation, we want this ICQ to be independent of beta. So for that, if RTH is less than 1 plus beta RE, we can see from this equation, if RTH is less, we can neglect this. So IBQ equal to is approximately equal to VTH minus VBE divided by 1 plus beta RE. So what is ICQ? Is beta IBQ. So beta VTH minus VBE divided by 1 plus beta RE. If beta is larger than 1, so 1 plus beta is approximately equal to beta, then this will get cancelled. So ICQ is approximately equal to BTH minus BBE divided by RE. Now we have got the IC current equation which is independent of beta. This is one of the main design equation. Next thing is, here we have just said RTH is less, should be less than 1 plus beta RE. So RTH it approximately is 0.1 1 plus beta RE. So this is one of the design equation which we have to consider for stability bias. This is one of the design criteria we have to consider for stability. This is the main design criteria we have to consider for stable biasing. Thank you.